All right, so I'm representing Team 6. So let me go to the beginning. So our proposal is called a Rota-Coolers proposal. So it evolved. So we started to talk about controlling the speed of sound in materials, about taking advantage of properties that will be based on internal rotation of dipoles, things of that sort. So we settled with a general idea. The objective of our project would be, as it says there, the development of a nano-cooler based on molecular scale organization. So I don't think there is a previous example of that, so we'll see how that works. So the idea is that we will take advantage of the dipolar molecular rotor arrays, and we will develop a nanocomposited cooler by taking advantage of the nanoscale electrocaloric effect. So the electrocaloric effect is really the physical principle behind this. So to optimize that, we will take advantage of a spontaneous order-disorder phase transition. That will help us have a large heat capacity, which translates in the largest temperature difference that you can accomplish. We came up with an idea. We wanted an application, and one application that we thought about is an autonomous swimmer as a prototype. So this is the electrocaloric mechanism, which is kind of interesting because this, I think, was intuitive for all of us, but we were not aware that it was a well-established principle. But this is what it is, right? So you have a collection of dipoles. This is the starting point, and they're obviously in an ordered state, so the system is diamagnetic. Now, the first step involves, you see here the field. There is an electric field, so these are two plates. Apply an external field, so this is at time 0. And over a certain amount of time, the dipoles will organize in the direction of the field. So basically what we're doing is we're reducing the entropy of the system from a high entropy state to a low entropy state. The next step is now that you're at this point, you remove the field, so you go back to E0. So the system returns to a more disordered state. And if you do that adiabatically, that's done at the expense of the heat of the system. So this is probably the one thing that we were all aware of. This is used with magnetic cooling when you want to cool, like sub-Kelvin, right? That when you want to go below 4 Kelvin, this is one of the main mechanisms. So doing a little bit of research, so we quickly discovered, you cannot see this table, but there is a couple of things. Unlike magnetic fields, which are very weak, electric fields have a much higher strength, so that instead of being at a few Kelvin or below, you can tune the interactions of your dipole and climb up to higher temperatures, including ambient temperature. This is a table of such materials, and all of these are actually ceramics, except for one you don't see here, but this is polyvinyl difluoride, and there are two lines at two different temperatures. At low temperatures, the delta T that you can reach per gram of material under some conditions is 6 Kelvin or 6 degrees. Under other conditions, when you reach the order-disorder transition, it goes all the way up to 20 degrees. So the figure of merit, if you want to call it that way, is significant. And the reason why you want to have that is because you want to have this transition, so this is a disorder-order transition, right? So there is a heat capacity associated with it that is larger. So there is this is the time where really you have the largest potential heat capacity that you can take advantage of. So it seemed kind of novel and interesting and never been done with a molecular system, and much less with a molecular machine, which in this case would be again, dipolar arrays. So the concept of the application is kind of illustrated in this picture, right? So let's say this is our cooler. So we figure, well, if we have a gradient, in this case a temperature gradient, we will have basically an opportunity to have a bending at some frequency. So this is a device that will exist between the capacitor plates that will help us execute the electrocaloric effect. And we're going to have another material here that basically is just going to be something that is a light absorber, something that has no fluorescence, no phosphorescence. It's all internal conversion, converts light into heat. So you had heating and cooling, and presumably under proper engineering, you have conditions where you can bend, and there is a number of questions that will have to be answered. But you can imagine that you can have, again, something that provides motion, and that motion could potentially lead to some sort of a swimmer or some nano agitator, something like that. We have a number of problems to solve. We need new materials with high entropy change at the specific transition. Again, this is the order-disorder transition. We need molecular dipolar rotor arrays that are able to adopt a phase-center cubic structure. That is because that spontaneously will adopt the ferroelectric state and will give us the largest order-disorder effect or ferroelectric paraelectric transition. The transition temperature needs to be tunable. That can be done basically by tuning the distance between dipoles and the strength of the dipoles, right? Short distance, large dipoles, larger dipole-dipole interactions, larger energies, higher temperatures. We're going to have to grow the materials, prepare the materials, characterize them, and build the sort of epitaxially grown structure. Market trends. So the need for cooling will be needed throughout the infrastructure of nanotechnology industries. So once if you have it available, you will use it, right? If it is not available, nobody will want to use it. So this fundamental technology will address the move away from current platforms. It should eventually allow cooling on all length scale and in the solid state. So impact. So the use of molecular machines to cool at the nanoscale will elicit ideas to construct multi-component nanoscale units. So we took this picture from the internet, and you can imagine that there probably will be devices out there that require a certain amount of temperature control at the nanoscale. In terms of visibility, so again, we need amphidynamic materials capable of displaying spontaneous order-disorder transition. So we want to be in this portion of the phase order diagram. Although it is not essential, in fact, we speculate that their heat capacities will be greater than those of most materials, because if they're rotary, then you'll have more degrees of freedom where you can actually have heat. And that really was what started to motivate our thinking, and we developed basically from that principle. Again, ferroelectric order will require phase-center cubic symmetry, large dipole moments. We estimate more than 6 dBi will be needed for transitions to occur at high temperatures. Dipole reorientation will require low-density structures with empty spaces. Prototype composites will require cooling and heating layers to grow epitaxially, so that, again, you'll have the opportunity to have that bending. Heating layer will rely on a chromophore that decays thermally so that it dissipates the light absorbed into heat. Expected results of, we want to find a versatile cooling solution based on molecular rotors. We will have characterized electrocaloric materials based on molecular rotors, so this is a new principle. Gain understanding of electrocaloric effects that is achievable, validate the concept and do the testing, build, validate the prototype, and test the prototype. Our milestones. So we are apparently a little bit lazy. We're not completing it in 2 years. We're going to go 5 years, but we got to market. So start synthesis of molecular components, build epitaxially rotary MOFs and photothermal crystals, test degree of electrocaloric effect macroscopically, prepare nanoscale materials. So, you get the idea. And this is our team. I think our team is also fairly diverse. There's some of us who are supramolecular solid-state chemists, engineers. I don't know what we all are, but we are pretty diverse. And I think that's all. So it was a lot of fun, I must say.
Wonderful, thank you. Stay up here.
Okay.
Let's see if our judges have any inquiries.
What's the temperature range that you're planning to cool down to?
Well, so the highest efficiency that we found, again, is about 20 degrees Kelvin, right? 20 degrees Kelvin. That's vinylene difluoride, and that depends on a relatively large heat capacity.
But are you planning on going from temperature to 20?
No, we ideally we were talking about doing it at round room temperature. So we would like to have it, at 300 Kelvin.
So from 300 to 20?
Right. So that would be the range, and so what that pardon?
For the same setup, are you going to go from 300 to 20?
That would be basically the range. So.
How do you plan to accomplish that?
So the temperature is determined by the position of the order-disorder transition, and the order-disorder transition depends on the dipole-dipole interaction. So.
All cryostats have more than one stage. All of them.
And so does this.
So that's why I was asking.
Yeah.
You go from what temperature to what temperature, and then
Right.
it's not clear to me that you can go in one shot from 300 Kelvin to 20.
It's a property of the system. It's intrinsic. It depends on the heat capacity. So whatever the heat capacity of the system is, that's going to tell us how much. What's going to determine the heat capacity is again the enthalpy difference between the order and disorder state.
The only system that I know of that can go from room temperature to around 80 Kelvin, and that's pretty low, is optical cryogenia. So that what you're talking is kind of true to me that you can do this.
So you have a heat source, right? A heat sink and a heat source. So if you're cycling, you're continuously cooling. So if you insulate the region that you're cooling, you can just continue. But we don't. That's not what we want to do. So we want to control a temperature range within a nanoscale structure.
Maybe I can comment on this.
Yes.
Actually, the beauty, I think, based on Miguel's materials is that you could change where this the cooling happens. So far, with all the known systems, you're stuck with whatever capacity they have. But here you can use chemistry to actually really shift it wherever you want to.
Any other questions from our judges? No, we're only doing judges right now.
All right.
Sorry.
Thank you.